So make sure that you have opened your packet to lesson 24 and starting off with this opening exercise in Lewis Carroll's Through the Looking Glass. Tweedledum says, the sum of your weight and twice mine is 361 pounds. Well, just from Tweedledum's sentence that he said, we're not going to be able to figure out how much Tweedledee and Tweedledum weigh because there's actually an infinite number of answers to that. But Tweedledee replies, the sum of your weight and twice mine is 362 pounds. Well, now we have enough information because we're going to have two equations with two variables to be able to solve this system. Okay, so if I start off with, let's start off with the sum. We'll make x equals to weight of Tweedledum. And we'll make y equals to the weight of Tweedledee. I usually use better variables in this, but there's not much way of telling the difference between Tweedledee and Tweedledum with letters, so I thought it would be easier just to use x and y. All right, so we got x and y. All right, so the first sentence that Tweedledum says, the sum of your weight, he's talking about Tweedledee, which is y, and twice mine, which so it's twice Tweedledum, so that's twice what x is 361 pounds. And the next sentence that Tweedledee says, the sum of your weight, well, that's Tweedledum's weight, and twice mine is 362 pounds. So now we have a system of two equations with two variables, and you have to choose how you are going to solve it. So I'd like you to go ahead and try to solve that equation to find the weight of Tweedledee and Tweedledum. You can choose, you can graph it, you can choose to use substitution, you can choose to use elimination, but do what you need to be able to solve and find the weights of Tweedledee and Tweedledum. So while there are different ways to solve this, I chose to use elimination. First I lined up the y's and the x's and the equal sign and the constants on the right, and then I multiplied the second equation by -2 because I decided to eliminate the x's. I saw that this was a 2x in this equation. I wanted to make this one a -2x so that when I add them together they are eliminated. So I multiplied the second equation by -2. I added them up, which eliminated the x's, solved for y, and I got 121. Then I took that value for y, plugged it in for the y in either one of these equations. I chose the second one over here and solved for x and got 120 pounds. So Tweedledum weighs 120 pounds and Tweedledee weighs 121 pounds. All right, now flip over the page, working on example 1. Lulu tells her little brother Jack that she is holding 20 coins, all of which are dimes and quarters. Well, that one sentence gives us one equation about telling us a little bit about dimes and quarters. I could let D equal dimes and Q equal quarters. And the next sentence will help me with another equation. They have a value of $4.10. She says she will give him the coins if he can tell her how many of each she is holding. So solve this problem for Jack. So the first sentence gives you one equation. The second sentence gives you a second equation. See if you can find the two equations with two variables and then check back. So my first sentence has the total amount of dimes and quarters added together must be 20. The second one has the value of the dime, 10 cents times every dime plus 25 cents times every quarter. Will give us the, should add up all of their values of all the dimes and quarters, should add up to $4.10. Now I'm going to ask you to solve this system of two equations with two variables however you would like. Just keep in mind it might be a good idea to try to eliminate the decimals first. So I decided to use elimination. I first multiplied the second equation by 100 to get rid of the decimal. Then I got 10d plus 25q equals 410. And then I decided to use elimination with the top one. So I decided to, in order to get rid of the d's, I needed to multiply the top 1d by negative 10 to make it negative 10d. And so I multiplied negative 10 by the whole top equation to get this, and then I added them together, which eliminated the d's, solved for q, and once I found q, plugged that back into the easiest equation was the d plus q equals to 20. I plugged in q 14 in for the q, solved for d, and I got 6. So Lulu has 14 quarters and 6 dimes. So for this next exploratory challenge, at a state fair, there's a game where you throw a ball at a pyramid of cans. If you knock over all the cans, you win a prize. The cost is 3 throws for $1, but if you have an armband, you get 6 throws for $1. The armband costs $10. So in the first part here, it says write 2 cost equations for the game in terms of the number of throws purchased. One without an armband and one with. So come up with, let's make C equal to the cost of playing the game, but in terms of T, the number of throws purchased. And see if you can come up with 2 equations, one for with the armband and one for without, and then check back and see if you have the same ones that I do. So without an armband, every throw basically costs a third of $1, since three throws cost $1. So the cost is equal to 1/3 of $1 times every throw. I could also write this y equals 1/3 x. And for with an armband, every throw costs 1/6 of $1 because 6 throws is equal to $1. But you also have to pay the initial $10 fee, so that's where the plus 10 comes in. I could do this as c in terms of t or y in terms of x. Y equals 1/6x plus 10. So now I'm going to ask you to graph those two, label the axes, and then answer the question after you've done that. Does it make sense to buy the armband? Oh, and you should definitely use some graph paper rather than on this orange paper because they don't have the squares inside there to make it easier to graph. Because I made the units on my x-axis the throws, and I made each square 3 throws, it made it very much easier to draw this graph because basically I was going by single dollars as the price was going up for either 3 throws or $1 for 6 throws. And since both 6 and 3 are divisible by 3, it made a lot of sense to make my throws here every 3 throws be on a square here. So for instance, when I made with the first one here, if I made no throws, I was at 0. And once I made 3 throws, it was $1. 6 throws was $2. 9 throws was $3. Whereas when with the armband, I had to start off with paying that $10 for the armband, but then it was every 6 throws, which is 2 squares, would go up $1. So another 6 throws, 2 squares would go up $1. And that would give me the slope of this one here and this line. And what I found was that only if I went past 60 throws would it make sense to buy the armband. Would the armband be a better deal? And that would be a cost of $20, which is a ridiculous amount to be paying on throwing a ball at a pyramid of cans. So I would never do that, so I would never purchase an armband. For this last one here, a clothing manufacturer has 1,000 yards of cotton to make shirts and pajamas. A shirt requires 1 yard of fabric and a pair of pajamas requires 2 yards of fabric. It takes 2 hours to make a shirt and 3 hours to make the pajamas, and there are 1,600 hours available to make the clothing. What are the variables? Well, basically what we're trying to figure out is how many shirts and pajamas we should make here, or we can make. And so those are the variables, the number of shirts and the number of pajamas that we want. So I'm going to write that in. And so what are the constraints here? Well, the constraints are that we have 1,000 yards of cotton and 1,600 hours to make the clothing. And here comes the challenging part. Now see if you can write the inequalities for those constraints. So we should have one inequality having to do with the material and one inequality having to do with the time. All right, once you have your inequalities, then let's graph it on some graph paper. Don't put it on this graph here. But the question is, which one do you want to make, the shirts or the pajamas, the X or the Y? Let's make the shirts the Y in this case here, and the pajamas the X. We could do either way, but it's just easier to solve for Y since the 1s there is easier to solve for in that particular inequality. So we'll make the shirts the Y and the pajamas the X. Go ahead and graph them and shade the region, and then we'll have to figure out what it means. So after solving each of my equations here for Y, and I made a scale of every square was equal to either 100 pajamas or 100 shirts, this is what I came up with for the graph. And I have a shaded area in here which represents all of the possible combinations of shirts and pajamas the manufacturer can sell. So that's going to try to figure out the next question, which I have in part 6 here, which is, suppose the manufacturer makes a profit of $10 on shirts and $18 on pajamas. How would it decide how many of each to make? So what I'm going to do is I'm going to look at here in terms of, I've made up an equation with my profit. I set that equal to 10 times the shirts plus 18 times the number of pajamas. Now, basically, I could basically try all the points in my graph that are possible points to see which one of these would give me the highest profit. But I know that it's going to be somewhere in here. It's either going to be one of my corner points here at the outermost part of this graph. It could be this point here, which is 800 shirts and 0 pajamas. It could be this corner point here, which is 400 pajamas and 200 shirts, or it could simply be 500 pajamas and 0 shirts. So if I should try each of those 3 points into this equation and see which of them is going to give me the most, that would help me decide how many of each the manufacturer should make. So go ahead and try that on your own and figure out which would be the best profit. So trying each of these 3 points into the profit equation shows me that to make the highest profit of $9,200, the manufacturer should sell 400 pajamas and 200 shirts.